wonder what really happens when you fine-tune a large language model? It's not just learning. It's a whole soap opera of tokens pushing, pulling, and sometimes getting squeezed out of existence. This paper dives deep into the learning dynamics of LLM fine-tuning, how training on one example secretly reshapes the model's behavior on others. It reveals why fine-tuned models sometimes hallucinate, repeat themselves, or even forget what they were supposed to prefer in the first place. And here's the twist. A weird little thing called the squeezing effect might be the culprit. Let's unpack how fine-tuning reshuffles probabilities and what we can do to fix the mess.
Let's start with the basics. You know how deep neural networks learn? By tweaking their internal parameters using gradient descent. It's all about adjusting those knobs based on mistakes. And that process, how each training example shapes the model's future predictions, is what we call learning dynamics. Researchers have used this lens to explain all sorts of training quirks, like why models zigzag toward better performance, or how abstract concepts emerge over time. But here's the twist. This paper applies that same idea to large language models, LLMs, during fine-tuning. That's when we take a pre-trained model and tweak it to follow instructions or align with human preferences. Most earlier work just looks at the end result, or how training loss ties to reinforcement learning goals. But this paper digs into the process, step by step, to see how individual examples reshape the model's behavior. They propose breaking each update into 3 parts, each playing a distinct role, and that sets the stage for understanding what's really happening under the hood. This framework helps explain weird fine-tuning behaviors, like why models sometimes degrade with more training, or start repeating themselves. And better yet, it might even help us design smarter training methods down the line. Now let's get into the math. The core idea is to break down how one training example changes the model's prediction on another. That's the learning dynamics at work. Think of it like this. If the model learns from one example, how does that affect its predictions elsewhere? The first equation shows a single gradient descent step. The model updates its parameters using the gradient of the loss, and that update shifts its prediction on some other examples. So the question is simple but powerful. After learning from one example, how does the model's confidence change on a different one? To answer that, they start with a classic supervised learning setup. The model predicts across a vocabulary by producing logits, raw scores, which get turned into probabilities. The key insight comes when they analyze the update for a single label prediction. They decompose the change in confidence into 3 parts. A matrix that adjusts based on the model's current belief, a kernel that measures how similar 2 examples are based on their gradients, basically, does learning from this affect that, and a direction vector pointing from the current prediction toward the desired labels. Stack these together, and you've got a formula that tracks the influence of a single training step. What's cool here is that this gives us a way to measure how training decisions ripple through the model's behavior, even on examples it never saw. Let's make this concrete with an example. Digit classification on NIST. Imagine training a simple neural network to recognize handwritten digits. This is where learning dynamics come to life. They assume that the influence of one training sample on others stays roughly stable over time. A fair assumption with small learning rates or lazy neural tangent kernels. Then, they break down how a single training example, say a digit labeled 4, affects predictions on other digits. Check out Figure 1a. The red arrows show the model adjusting its internal prediction, pulling the probability toward 4. Now, what happens to other inputs? Figure 1b explores 3 cases. Test on another 4, and confidence jumps. Test on something visually similar, like a sloppy 9, and you get a smaller boost. But test on something totally different, like a 1, and the update barely matters. Here's where it gets interesting. Figure 1c shows what happens after many updates. Visually similar digits, like 4 and 9, start pulling each other's predictions up. Even though the model only trained on 4s, it gets more confident on 9s just by association. That mutual influence stacks up, and the heat map in Figure 1d shows it clearly. The off-diagonal squares light up, revealing which digits the model confuses or connects based on visual similarity. This is the power of learning dynamics. It explains not just individual steps, but how they build into emergent behavior. Now let's shift from digits to language. Here, the model isn't just predicting a single label. It's generating full responses, one token at a time. That adds complexity, because each prediction depends on all the previous tokens. So the learning dynamics get trickier. The paper starts with supervised fine-tuning, or SFT. A model learns from prompts and their expected responses, using negative log likelihood loss, penalizing low probability assigned to the correct next word. But since we're dealing with sequences, this probability is calculated token by token, conditioned on all prior ones. To handle this, they pack the sequence into a single input and use masked attention, so each token prediction can't peek at the future. Once the sequence is packed and masked, they extend the earlier influence decomposition to handle every token in the sequence. And here's where it gets deep. They derive a new formula, breaking down how the prediction on one sequence changes based on learning from another. It stacks 3 ingredients for every token: sensitivity to changes, similarity between examples based on gradients, and how far the current prediction is from the desired one. The result? A layered view into the learning process. This lets them ask sharp questions, like, if the model sees one good response, how does that affect its opinion of another? And that's crucial for understanding generalization and overfitting in LLMs. Now let's talk about preference tuning, where the model learns not just what's right, but what's better. Unlike SFT, which tells the model exactly what to say, preference tuning teaches it to rank responses. That's where direct preference optimization, DPO, comes in. Here's the idea. You take a prompt and 2 responses, one preferred, one not. Then, you train the model to boost confidence in the preferred one and suppress the others. The DPO loss balances how much the model prefers y_+ over y_-, compared to a reference model, usually the SFT-tuned one. To understand how this changes behavior, the authors break down the DPO update like before, with a sensitivity matrix, a similarity kernel, and a residual vector showing how off the model's beliefs are. But here's the twist. Now we have 2 responses. So there are 2 influence terms, one pulling up the preferred response, one pushing down the rejected one. How strong these forces are depends on how well the model already separates the 2. If it already prefers the right one, the gradients shrink. If it's still confused, the updates hit harder. And this leads to a weird side effect. When you push down too hard on an unlikely answer, things can go sideways. That's the squeezing effect, and it's up next. Here's where things get weird. Ever notice how sometimes pushing a model too hard on its least likely answers backfires? That's the squeezing effect, and it's a big deal in alignment. Take a look at Figure 2. The left panel shows SFT, gentle nudges toward better responses. Nothing crazy. But the middle panel? That's where DPO gets wild. It applies a steep gradient to a preferred response, even if the model initially thought it was unlikely. This strong push in a low-confidence region, a valley, distorts the whole prediction distribution. It doesn't just boost the good answer, it squashes everything else. This squeezing leads to some odd trends. The model becomes less confident overall. The predicted distribution piles onto the most likely answer, no matter what the training label says. Tokens with low probability get crushed even further. It's like the rich get richer, and the poor get poorer. And here's the kicker. This isn't just theory. Recent work shows that during DPO, confidence drops for both preferred and rejected responses, totally unlike SFT, where good answers stay strong. The takeaway? Alignment with strong gradients, especially off policy, can backfire by warping the whole prediction space. Time to test if this holds up in practice. The authors take 2 real-world datasets, Anthropic-HH and Ultra Feedback, and train models using SFT or DPO. Each training point has a prompt, a preferred response, and a less preferred one. They build a big training set, 5,000 samples, and a special test set, 500 samples, to probe model behavior. Here's the clever part. For each prompt, they generate multiple test responses, the less preferred one from training, a rephrased version of the preferred one, or even a random English sentence. This lets them study not just whether the model prefers a learning_+, but how that learning spills over to similar responses. For SFT, the key observation is that training on a good response boosts confidence in similar ones too. It's like how learning 4 in MIST nudged up 9. This spillover is strongest early in training, when the model hasn't seen these test responses yet, but still shows higher confidence. Why? Because they're similar enough to the training response. The kernel values are high. Over time, this indirect influence fades, but early on, it's a clear sign of learning dynamics in action. Let's zoom in on SFT's broader effects. When the model learns to prefer one response, what happens to the rest? Figure 3 tells the story. Training on a preferred response steadily boosts confidence in it. But similar responses, rephrasings, or slight variants also get a lift. It makes sense. If you teach someone to like one phrase, they'll warm up to similar ones too. That's the pull-up pressure. As the model gets more confident in a C_+, the probability mass has to come from somewhere. So the rest? They slowly get pushed down. To test this, they throw in wild cases, random English or scrambled versions of the preferred answer. These get no lift and just keep falling in confidence. That's push down in action. But if a response was seen during training, even indirectly, resists the fall, which might explain why some hallucinations stick around. The last heat map panel shows how influence spreads. Responses with shared structure or phrasing form hidden clusters. Fine-tuning one affects the whole group, so training on _+ might unknowingly shift the model's opinion on a dozen similar phrases. This sets up a big question. If SFT does all this shifting, how does DPO behave when applied afterward? Now let's dive into DPO's quirks. Figure 4 lays it all out. They run similar experiments as before, but with off-policy DPO, and track how different response types evolve. First panel. Confidence in the preferred response rises, as expected. But its rephrased versions? They climb more slowly. DPO's gradient is laser-focused on the exact string it's trained on, unlike SFT, where influence spreads more broadly. Second panel. The rejected response drops fast, faster than its rephrased cousins. The negative gradient hits hardest on the exact training example. But in the third panel, those rephrased rejects still take a hit. Being too similar is enough to get dragged down. This shows how influence generalizes across the model's latent space, guided by that similarity kernel. Fourth panel. The margin between preferred and rejected predictions grows with training. Good. The model is learning to separate good from bad. Fifth panel. Here's the squeezing effect in full force. Strong gradients on unlikely outcomes don't just boost the preferred answer, they flood the most likely one. That's not always ideal. And it explains DPO quirks like repetitive or generic responses. Now let's tie it all together. The authors propose a simple fix for the squeezing problem. Preemptively boost the model's confidence in unlucky responses before DPO hits them. They call this the extend method. Here's how it works. During SFT, they don't just train on preferred answers. They also include some rejected ones, especially those at risk of being too unlikely. That way, when DPO starts, those responses aren't at the bottom of the distribution. The negative gradients aren't as extreme, and the model avoids over-squeezing. Figure 5 shows the results. The baseline and extended models behave similarly on preferred responses, but on rejected ones, the extended model starts with higher confidence during SFT, setting it up for a gentler DPO ride. It also slows the collapse of confidence on irrelevant responses and keeps the top prediction from dominating too much. And it works! Table 1 shows extended models consistently beat the baseline in win rate tests, especially against ChatGPT. It's a great example of how understanding learning dynamics leads to small tweaks with big impacts. To wrap up, learning dynamics explain fine-tuning quirks, from hallucinations to degeneration. And by digging into how gradients interact with unlikely outcomes, they've found a fix that's both practical and effective. Thanks for joining us today. Happy exploring!